Okay, our last little video on kinetic energy and what kinetic energy actually is in Newtonian mechanics will be the proof of the work energy theorem in the general case. Okay, so we have this definition that work is going to be equal to the integral of f dot dx, where these are both vectors. Okay, and so we sort of figured this out last time what this actually is, but let's see if we can take this and actually get an idea, because remember we have that the kinetic energy was defined as being 1/2 mass times velocity squared. So can we relate that to this? So let's see what we can do here. So the first thing is using Newton's law. So Newton's law says that F is equal to ma. So we have F is equal to mass times the acceleration vector dotted with dx. Okay, and then we're going to do something similar that we did when we were looking at a constant force. The only difference that we're going to do now is that we're working with vectors instead of with just average accelerations. And so what we're going to have the integral of the mass times. Okay, what is the acceleration? The acceleration is the change in the velocity vector dt. That was a definition that we had, and that's going to be dotted with what? This dx. Now, it turns out to be a property of vectors and of dot products that when we have a scalar, we can move it from one to the other. So the way that we can rewrite this is we can rewrite this as the mass of dv times dx dt. And this is really, I should be a little bit more careful here. This is actually a dot product, so I want to put a big dot here just to make sure that we're doing things right. We have dx dt. Okay, and this dx dt, this piece here, that's just the definition of velocity. So that's just our standard velocity. So we can rewrite this whole thing as the integral, which I dropped my integral sign, so I need to put that back. I have the integral of the mass times the velocity dotted with the now infinitesimal change in velocity, dv. Okay, so this is the thing that we need to solve. Now, if you go back and look at our definition of what a dot product is, so if we take A dot B, this was in the algebra of vectors video, what we found was that that's going to be AX plus BX, AX times BX plus AY times BY plus AZ times BZ. Remember, you just take the components of each of these vectors and multiply them component-wise, then add them together. So let's do that exactly here. So what we're going to have is we're going to have the integral of the mass times what? We're going to have Vx, the x component of the velocity, times dv times dvx. And then we're going to add to that Vy times dVy. And then we're going to add to that Vz times dVz. Now, we have gone from a vector equation with the arrows to a scalar equation. Remember, the components of a vector are just scalars. This is part of the reason this thing's called a scalar product. So this is no longer a vector equation. It turns out that the integral symbol is actually distributive. So the way that we can rewrite this is we can rewrite this as the integral of the mass times Vx dx, dvx, plus the integral of the mass times Vy dvy, plus the integral of the mass times Vz dvz. So in other words, we can separate the integral and put it over each portion here. Now, you'll have to take a little bit of calculus to learn this next step. But the next step is how to actually take these integrals. When you have the integral of a constant times a function with an incremental change of that function, how do you calculate this? It's not hard, but I'm not going to prove it here. That's just calculus. And so the calculus will give you that what we get in each case is the mass divided by 2 times Vx squared. And we have to integrate that from wherever we start, which we're going to call position 1, to wherever we finish, which we're going to call position 2. So each one of these integral signs has implicitly, I've put a 1 and 2 there, and you can go back and put them in on the rest of them yourself. But we're going between position 1 and position 2, so that would be V1 to V2. So we're going from 2 to 1, or V2 to V1. Okay, and we get the same thing for the other 3. So we end up with m over 2 v y between 2 and 1 squared, and then plus m over 2 vz, and that would be again squared, and from position 2 to position 1. All right, so there are some like terms here. All these have a mass over 2. I can factor that out. So I can take a mass over 2. And I'm going to get Vx2 squared minus Vx1 squared. So I'm going to get something, I'm going to write them this way. Vx2 squared minus Vx1 squared. So this is the velocity at the final position minus the velocity at the initial position, both of which are squared. And then we get the same thing for each one of these. So over here I've got a plus Vy2 squared, and I've got a minus Vy1 squared, and I've got a plus Z2 squared, and a minus Vz1 squared. And notice this one, I can put this in parentheses and just put plus signs here. So in other words, I factor out a negative sign. So I get Vx2 squared plus Vy2 squared plus Vz2 squared. Well, what is that? That's just the total magnitude of the velocity. This is just this is the total magnitude of the velocity at the second position. So we can rewrite this whole thing as being m over 2 times v2 squared minus, and this is Vx1 squared plus Vy1 squared plus Z1 squared. That's just the total velocity at position 2. At position 1. So V1 squared. Or in other words, we can rewrite this as mv2 squared over 2 minus mv1 squared over 2, which is exactly our definition of kinetic energy, which is T2 minus T1, or the change in kinetic energy, change in delta T. So what we have proven from way back here, our definition of work, so this is the proof of the work energy theorem. Let's write down the equation. That the work done is equal to the area underneath the force displacement curve, the area underneath the force displacement curve, and that's going to be equal to the change in the kinetic energy. Incredibly important equation for archery, because this tells you how much work your arrow can do. Your arrow can only do as much work as it has kinetic energy, because the other forms of energy that the arrow might have are not available for doing penetration type work. So delta T, the change in the kinetic energy, or the change that occurs in the kinetic energy, will be the same as the work done by the arrow during a penetration process, and that's proven by this work energy theorem.